Rajeshwari MJ. She pursued her BE in Electrical and Electronics at the People's Education Society College of Engineering, Mandya. She pursued her MTech in VLSI Design and Embedded Systems at the Sri Jagadguru Balagangadharanta Institute of Technology, Bangalore. Her personal skills lie in good verbal and written communication skills. Her areas of interest lie in OOPS with C++, renewable energy sources, HVDC transmission, digital relays, automotive electronics, advances in VLSI design. She has also had papers presented at the national level, such as the Innovative Architecture for SoC Multi-Core Hybrid Processor, presented at the RNSIT, Bangalore.
Welcome to UGC lecture series of BSc Applied Electronics. Today we are dealing with the subject Semiconductor Devices and Integrated Circuits. Let's start with the Unit 3 Field Effect Transistor Part 2. Today we are going to discuss about the topics of metal oxide semiconductor field effect transistor and its characteristics and working, construction, and also its drain characteristics, and also the JFT and MOSFET comparison. Let's start with the MOSFET definition and the types of MOSFET. MOSFET is a metal oxide semiconductor field effect transistor that can be operated in a enhancement mode and as well as a depletion mode. What do you mean by enhancement mode and depletion mode? Depletion mode in the sense when the transistor is operated below the VGS, when VGS is lesser than 0 or equal to 0, it will going to operate, that is there will be ID current, that is drain current will be exist when VGS is lesser than 0. At that mode it is called as depletion mode, when a transistor will going to operate in a voltage lesser than 0 or equal to 0. And what do you mean by enhancement mode? In enhancement mode, the transistor operates only when the gate to source voltage is greater than 0. There will be no ID current if it is lesser than 0. And since there are more difference between enhancement mode and depletion mode, this is the basic one. We will study further about the difference of depletion and enhancement mode. Let us start with the types of metal oxide semiconductor field effect transistor. It has depletion type MOSFET and enhancement type MOSFET. In depletion type MOSFET means the MOSFET which will going to work in depletion mode and as well as enhancement mode. That type of MOSFET we called as DMOSFET or depletion MOSFET, and another type is enhancement MOSFET. In enhancement MOSFET, the MOSFET will going to operate only in enhancement mode, that is why it is called as enhancement MOSFET or eMOSFET. Next we start with the DMOSFET. What do you mean by DMOSFET? How it looks like, what is the structure? Let us know about DMOSFET. In the DMOSFET, from the figure we can observe from the N channel DMOSFET. N channel DMOSFET, there will be N bar. There will be two type of material, one is N, another one is P. P is called as a substrate and N is a one more bar. N type, either terminal is named as drain and source. There is a gate which is insulated with silicon dioxide layer. On top of it there is a metal contact. This is the major difference of metal oxide semiconductor and field effect transistor, where we call metal oxide semiconductor field effect device because it is having a insulated gate. It is insulated with a silicon dioxide layer. That is why it is called as metal oxide semiconductor field effect transistor. This type of MOSFET is called as N channel because there is a N channel in between the P gate and P substrate. The N channel is formed. We will study in the operation how this N channel will form when we are going to bias the MOSFET. And this MOSFET will having the same as in case of FET, it will having 3 terminals: drain, gate and source. Usually this is not a terminal, the substrate is shorted with the source internally. There will be only 3 terminals, one is drain, gate and source. The DMOSFET will going to operate both in a enhancement mode and as well as a depletion mode. Next we move on to eMOSFET. What do you mean by eMOSFET? How it looks like? come from the figure, we can observe the difference between E MOSFET and D MOSFET. There will be no channel here. The P substrate is extended till the insulated layer silicon dioxide, that is why there will be no channel, but for reason when it is operating, as we increase the gate voltage, there will be a formation of channel here, okay, that is not visible. So, it is called as included channel, that is we are going to make channel by applying gate to source voltage, that is what is called as included channel. This is the N channel E MOSFET. Here also when we apply the gate voltage, the channel will be N channel, that is why it is called as N channel E MOSFET, and it is also having the silicon dioxide layer. The gate will be of metal contact and it is insulated with the silicon dioxide layer, and it as having a 3 terminal drain, source and gate. The substrate is shorted with the source internally, and the symbol for N channel D MOSFET. N channel D MOSFET, the structure we already come across with this. This is how it looks, and the symbol is like this. It is having 3 terminal, mentioning 3 terminal drain, gate, source. This is the substrate. This another form we can also represent like this. The substrate can be shorted with the source. This drain and source terminal can be interchanged, and this is the direction of the current. And here one more thing we can observe, the gate is looks like a capacitor here, but when it comes to FET, junction field effect transistor, JFET, the gate looks like a reverse diode. That is why here the gate will exactly look like a capacitor, and also it acts like a capacitor. How the gate will going to operate, how the electrons and holes are placed, here we study in a operation of a D MOSFET. Next we move on to symbols of P channel D MOSFET. In a P channel D MOSFET, the only difference is here N channel, this part the substrate will be P type and the bar will be N type. Here in the P channel, this bar will be P type, the substrate will be N type. So, P type means P channel will be found here, that is why it is called as P channel D MOSFET, and the symbol will be represented like this. Same thing, gate, drain and source. This is the current direction we are showing on the substrate, and another symbol which we can represent as like this, where the substrate is shorted with the source. These are the symbols of P channel D MOSFET. Next, circuit operation of D MOSFET. In the D MOSFET, as we know, it will going to operate both in a enhancement mode, and that is VGS is lesser than 0 or equal to 0, or it can operate in enhancement mode, that is VGS is greater than 0. So, when we are going to give a negative voltage, we can call that operation as a depletion mode operation, and when we give a positive voltage, positive gate to source voltage, that operation we called as a enhancement mode operation. That is why we call this operation as a depletion mode operation. The biasing of a depletion mode D MOSFET, it looks like this. Here the drain, the gate to source is reverse biased, as in case of FET also we reverse bias the gate, here also we reverse bias the gate, and the substrate is shorted with the source, and this is a drain voltage. This is how it looks when we are bias the D MOSFET. And when we are going to bias a D MOSFET, when we increase the reverse voltage, when we are going to apply the VGS, that is VGS is increased, this reverse voltage is increased, the free electrons will going to place in the gate region like this, and across the insulator what happens, since there is a pre-substrates, the electrons are the minority carriers, less number of free electrons here. So, the poles, the holes in this N type regions will come and occupy next to the silicon dioxide layer, and it will going to make the free electrons depleting, that is it will makes the conductivity will be going to decrease due to the less number of free electrons. Since the availability of electrons is less, the resistance will increase and there will be no current. This when we are going to increase the reverse voltage, the conduction will be less. That is what we can observe when we are going to give the gate to source voltage of reverse voltage. Next we move on to enhancement what we can infer from the figure is greater the negative voltage, lesser will be the source to drain current, because as we increase the reverse voltage, the channel will go on decreasing. Since the width of the channel will go on decreasing, the possibility of current is lesser. So, as we go on increasing the reverse voltage, there will be decrease in the drain current. Next we move on to enhancement mode. Here also we can observe few things. That gate is here positive, that is in enhancement mode we are going to give positive VGS. Here it is positive terminal which is connected for the gate, and also substrate is shorted with the source. Drain will be having a positive voltage VDD. When we going to increase the VGS, the positive holes will come and occupy the gate terminal like this. We will going to arrange the gate layer like this, and next to the silicon dioxide layer, the available free electrons, the available plenty of free electrons will come and occupy here, which will going to attract each other, because of unlike a charge pole, positive charge carriers will occupy here and the negative electrons will come and occupy here. This will make more free electrons available in the n type region, and also the channel width will be increased. Since the channel width will be increased, means the resistance is decreased. As the resistance decrease, the current will be increased. So, this is how when the MOSFET will going to work in a enhancement mode. Some of the points that we do note down about the DMOSFET, that is depletion MOSFET. Now come across the depletion MOSFET operation, how it works in a two mode, because it will going to operate in both the mode, in an enhancement mode as well as depletion mode. So, some of the points we need to remember of DMOSFET operation are: the source to drain current is controlled by the electric field of capacitor formed at the gate. That is what the gate is exactly like a, it acts like a capacitor. So, the electric field of the capacitor will varies the gate, the drain current. So, as we increase the electric field, the width of the channel will going to be increased. Since it increased, the resistance is decreased and the drain current also increased. So, by varying the electric field, we can control the drain current. Next, the gate of JFET behaves as a reverse bias diode, but where in a DMOSFET it will act like a capacitor. This is what the major difference of JFET and DMOSFET. As the gate of DMOSFET forms a capacitor, therefore, negligible gate current flows whether positive or negative voltage is applied. As we know, for a MOSFET we can apply, for a DMOSFET we can apply positive as well as negative voltage. So, when we are applying positive or negative voltage, since the gate is act like a capacitor, there will be negligible gate current flows here. This is one of the major point, and extremely small dimension of the oxide layer under the gate terminal results in a very low capacitance, and the DMOSFET has therefore a very low capacitance. Since insulation layer, the silicon dioxide layer very small, so the DMOSFET will have very low input capacitance. These are the points that we need to remember about the DMOSFET operation. Let us have a short break. Welcome back after a short break. In the previous session we are discussing about DMOSFET and its operation, and which are the important points that we need to remember in a DMOSFET operation. So, next we move on to DMOSFET transfer characteristics or transconductance characteristics. What is the transfer characteristics of DMOSFET? It is a curve where we are going to draw the ID current across the VGS, negative VGS. The curve here shows the IDSS, that is shorted gate to source drain current. When we going to short, the gate to source is shorted, the VGS is equal to 0, the maximum current, the maximum drain current at VGS is equal to 0 is called as IDSS, the shorted source drain current. This is what we can observe, and here we can also observe when we are going to decrease the VGS, the ID will be decreasing, the current will be decreasing. This and this portion is called as depletion. As we decrease also, there will be some sort of current in the negative. When the VGS is less than 0 also, there will be some value of current. That is why this portion is called as depletion region. This is where the D MOSFET will operate in a depletion mode. So, that is when ID is lesser than IDSS. As we increase the VGS, as we increase the gate to source voltage, the IDSS will increase and reaches a maximum value. The gate to source voltage, when the ID reaches maximum value, after that it reaches a constant value here. That point is called pinch off, as in case of FET. And here we come to know this, when VGS is greater, the IDS also increases. This mode is called as enhancement mode. When ID is greater than IDSS, the transistor D MOSFET will operate in a enhancement mode. Another case, when VGS is touches 0, the D MOSFET will completely in a cut off mode. That is, we can say that D MOSFET in off mode, that is in off condition. This is what we can observe from the conductance characteristics or transfer characteristics. So, next the transconductance curve that what we observed in a D MOSFET is similar to JFET. So, the drain current is also same as a JFET, that is ID is equal to IDSS 1 minus VGS divided by VGS of whole square. This is what we get the drain current for a D MOSFET. Next we move on to enhancement MOSFET. As we know, this MOSFET will going to work only when gate to source voltage is greater than 0. Let us look at the circuit when it is going to biased, what happens. First we consider when VGS is equal to 0 condition. When we are not going to apply gate to source voltage, there will be no channel. There will be no channel, already we know that in the structure itself we know the P substrate is completely penetrated and it touches the silicon dioxide layer. We know channel, and there will be no free electrons to conduct from N to N region, from drain to source region there is no free electron. So, the ID is completely 0 when VGS is equal to 0. This is what we observed when VGS is equal to 0, that is the first condition of E MOSFET operation. Next we move on to another condition when we are going to apply VGS. When VGS is positive, there will be a available of electron minority charge carriers of P type material, that is the free electrons will be have in the P type, that is less number. That less number of free electrons will be attracted by the gate, because on top of gate the positive holes are deposited. This will going to attract the minority carriers of P type material, and the electrons comes lay down in the below the insulated layer. So, it forms a channel, that is what we call as a included channel. This included channel will form the voltage at which the conduction of a E MOSFET will takes place is called as threshold voltage. The minimum voltage required for a E MOSFET for the conduction purpose is called VGSTH, that is threshold gate to source voltage or threshold voltage of E MOSFET. Once the VGS reaches the threshold voltage, the conduction of electrons will takes place from drain to source due to the formation of included channel here because of the minority carrier from the P type material. As we increase the VGS further above the VGS, the ID will go on increasing, and it exactly look like what we studied in the D MOSFET enhancement mode. In the curve characteristics of the D MOSFET, in the first curve what we studied, it exactly increases the current as we go on increasing the gate to source current. This is what we observed from the E MOSFET operation. Next, one more thing, how we are going to turn off the E MOSFET. As we go on increasing VGS, we know ID will increases. As we go on in decreasing below VGS-TH, that is below threshold voltage, there will be no current, ID will be 0 in E MOSFET. This is the important thing, that is where in a depletion mode we can observe below this VGS also some current, but here below the threshold voltage there will be no current, ID will be completely 0 here. Next, some of the difference of D MOSFET versus E MOSFET, that is what we studied till now about the D MOSFET and E MOSFET, how the schematic symbol is different. This is how the depletion MOSFET is represented, but the E MOSFET is represented like this. The depletion layer will be represented here completely in a thick line, but here it is broken down, that is why it is called as E MOSFET. This is a major symbol difference of D MOSFET and E MOSFET. When it comes to transconductance curve, we can observe current when VGS is lesser than 0, that is below 0. Also we can observe the current, ID current, but here we won't observe any current when VGS is lesser than 0. This is the difference of transconductance curve of D MOSFET and E MOSFET. When it comes to operation, there is different mode of operation for D MOSFET. We know that the D MOSFET will going to operate both in depletion mode, that is VGS is less than 0, and also it operates in VGS is greater than 0, that is enhancement mode. This operate in both depletion mode and enhancement mode, but enhancement MOSFET operates only in enhancement mode. And why this enhancement MOSFET is called as enhancement? Because as we increase the gate voltage, the conductivity will going to increase, the conductivity will enhance, that is why we want to use the word enhance. Here in the depletion, as we increase the voltage, during the negative voltage we are going to deplete the channel, we are going to deplete the depletion layer, that is why it is called depletion mode or depletion MOSFET. Commonly used bias circuits. Some of the commonly used bias circuit for D MOSFET are gate bias, and self bias, voltage divider bias, zero bias. And next one is gate bias for E MOSFET, which is similar to D MOSFET, and voltage divider bias and drain feedback bias. This is the difference. The voltage divider bias is same as D MOSFET, the difference is drain feedback bias is one more new thing that we are going to use in E MOSFET. Next, D MOSFETs over JFET. This is what the JFET we are studied in the part 1 of unit 3. We compare the JFET, junction field effect transistor, with the D MOSFET. Let us see how both of it are different from one another. The schematic symbol, the JFET schematic looks like this. This is a N channel JFET. This is a D MOSFET, that is what depletion mode MOSFET, N channel depletion MOSFET. This is N channel junction field effect transistor symbol. Next, transconductance curve or transfer characteristics curve. In JFET we will going to operate in depletion mode only, that is what we can observe from the curve. As we increase the VGS will operate from the negative. We know that in JFET we are going to give the reverse voltage. So, that is why we can consider that JFET will be works only in a depletion mode, in a negative voltage. When we increase the negative voltage, it reaches the ID current will going to reach the IDSS. That is what when we observe in a transconductance curve, ID reaches the IDSS, the VGS will be, the VGS is 0 here. And also when VGS is going to decrease, the ID current will become 0, and when it reaches IGS off or IGS cutoff, that is gate to source cutoff voltage, the ID current will completely 0. And when it comes to D MOSFET, it will going to operate in depletion mode and enhancement mode. That is when VGS is less than 0 also there will be current, and VGS is greater than 0 also there will be current, and when ID become IDSS, the VGS is 0. This is what we can observe from transconductance curve of JFET and D MOSFET. When it is come to commonly used bias circuits, The JFET is commonly biased with gate bias, self bias, voltage divider bias. But in D MOSFET we use all three types, which is similar to JFET, but one more thing, that is zero bias. Zero bias also exists in D MOSFET. And advantage, extremely high input, that is what we need JFET rather than BJT, that is what we need. So, extremely high input impedance and higher input impedance than comparable JFET. This is having a high input, but this is having even more higher input compared to JFET and can operate both modes. It is operating both in depletion and enhancement. And the disadvantages, bias instability is the biggest disadvantage of JFET. Here also same thing, and can operate only in the depletion mode. That is the main thing, that it can operate only in the depletion mode, only in the reverse or negative voltage it will operate, but here it will operate both in positive as well as negative, and it is more sensitive to changes in the temperature than JFET. The D MOSFET will going to change with the temperature, but not the JFET. Next comes with a summary, that what we are studying till now is MOSFET and its different types, enhancement and depletion, and in depletion N channel and B channel, and in enhancement N channel and P channel, and we studied the D MOSFET operation, its transconductance curve, how the ID will increase and decrease with increase in VGS, and also next we come across with the ID current, and also we studied about enhancement operation and its transfer characteristics, the difference of two types of MOSFET, that is E MOSFET and D MOSFET, and finally we discussed about the difference of JFET and MOSFET, and I hope that we come to know about the different type of transistor, different type of field effect transistor, and different type of MOSFET. These two things that we learn in this session. Next is questions. What is the basic difference between D MOSFET and E MOSFET? What is the need to develop MOSFET? Next, the references. For the reference, you can refer the website www.talkingelectronics.com and Electronic Devices and Circuit by G.K. Mittal. This ends the session. Thank you.